In the next 5 or so years, it is expected that nearly 50 billion electronic devices will be utilized to perform everyday tasks such as sensing environmental and monitoring health conditions, which all require a constant source of energy. This growing number poses a technical problem of how we can power these devices in a sustainable manner. Energy harvesting aims to tackle this issue as energy harvesters scavenges readily available energies from our environment that we normally do not use. But the problem is that these are mostly rigid structures, meaning we cannot use them to power wearable devices as this would require them to be flexible and shape adaptive. One solution to this problem is through the use of triboelectric nanogenerators, which was first discovered by Zhonglin Wang from the Georgia Institute of Technology. From its discovery in 2012, its output power density improved significantly within just 6 months, from a mere 3.67 milliwatts per meter square to almost 313 watts per meter square. It also has a high energy conversion efficiency of nearly 72%. More recently, these devices have been fabricated in such a way as to make them both flexible and biocompatible, which could be attached to curved surfaces such as the human skin or even human organs that could continuously scavenge unused mechanical energies our body produces every day. The principle behind this technology is the phenomenon called the triboelectric effect. Essentially, when the surfaces of two different materials are put close to each other, electrification occurs at the interface and generates the same amount of charges with opposite polarities on both surfaces. As these surfaces are slowly separated, a potential difference is generated. In order to balance this, the same charges must accumulate on the electrode interface, which would lead to a current flowing. The same is true when we try to place these two surfaces in contact again, only this time the current produced is in the opposite direction. So the first part is analogous to charging a capacitor, while the second one is analogous to discharging a capacitor. If we repeat the whole process, an alternating current or AC is produced. Now the type of material used is crucial in order to maximize the voltage output. Ideally, you would want one surface to be tribo-positive and the other to be tribo-negative. And the farther apart these two materials are from each other in the triboelectric series, the higher the voltage generated is. So the triboelectric series ranks materials according to their tendency to either gain or lose electrons. With their device, they were able to demonstrate how finger tapping, with a tapping frequency of 1 to 2 Hz, is enough to power an electronic watch. The device is also highly sensitive to pressure, as it can detect pressure as low as 1.3 kPa, and so it can be used as a touch sensor. What's new in their study is that they fabricated the device in such a way as to provide it with new functionalities. Here, they fabricated a triboelectric nanogenerator composed of an ionic hydrogen film sandwiched between two elastomer films. So instead of using electrical conductors as previous studies have used, here they use ionic conductors. Because the materials used are stretchable and transparent, the final device is also stretchable and transparent as well. And by selecting appropriate hydrogel elastomer combinations, one can achieve specific stretchability and transparency requirements. For example, they were able to fabricate a device that can be stretched 11 times its original length. It was also shown that in its stretched state, the device produced higher voltage. And this is because an increase in the material's surface area leads to an increase in the contacting area for electrification. Also, when the device was allowed to revert back to its original length, the voltage output was maintained as before, which suggests no degradation of the device even after being stretched. Finally, the device is also biocompatible or non-toxic, meaning it can be safely implanted to living tissues or organs. The patent for the triboelectric nanogenerator was filed in the year 2014, but it wasn't until 3 months ago when it was finally approved. Aside from the contact separation mechanism shown earlier, they also introduced another mechanism called the sliding mechanism, which also produces the same result as the first one. Figures 5 and 7 shows a possible design for the sliding mechanism, wherein the rotation of a cylindrical shell or disc would lead to two surfaces sliding past each other. As mentioned in the first slide, most energy harvesters scavenge energies from our environment, but those methods pose limitations in terms of portability and flexibility. Triboelectric nanogenerator provides a solution to this problem by introducing new functionalities that can act as both energy harvester and tactile sensor. Similar to piezoelectricity, these devices can be used to scavenge mechanical energies, say a person produces when they walk. We could also take advantage of the fact that the device is transparent, so we can attach it to LED screens, which would be enough to power them from the energy finger pressing generates. We can also scavenge mechanical energies produced within our body, such as powering pacemakers using the beating of a person's heart. Finally, this could be incorporated into a wireless system that can be used in medical operations such as laparoscopy, as it is both pressure sensitive and biocompatible.